All right, fine. Let's talk about the temperature dependence of K and how Gibbs free energy has a role in that. So when we're talking about K, remember we're talking about every single temperature has a certain K. And as the temperature changes, the value of K changes. So let's take a look at that. But first, let's start off. We know that the delta G of the reaction at standard state is negative RT ln K. And then we also know that the delta G of the reaction is equal to the enthalpy of the reaction minus T delta S of the reaction. So we can see both of these things are equal to delta G, so we can set them equal to one another. This right-hand stuff we can set equal to one another, and when we go, let's just go ahead and do that. Negative RT ln K is then equal to delta H of the reaction minus T delta S of the reaction. We're going to divide both sides by negative RT. You'll see why in a minute here. And so this on this side, it cancels out to just be ln of K. This one we'll write as negative delta H of the reaction over R times 1 over T. You'll see why we wrote it that way in just a second, plus this then delta S of the reaction over R. And so why do we write the equation like that? Well, if we think about what this equation could be, it could be equal to y equals mx plus b, and indeed is, right? This is your y. This is your slope right here. This is your x right here. And so this is your delta S right here. So you can plot values of the ln K versus 1 over T to find the delta H of the reaction and the delta S of the reaction. So for instance, if you wanted to know that the enthalpy of a certain reaction, the standard enthalpy of the reaction, then you could do your reaction at a certain temperature, increase the temperature, rewrite what K is, plot that versus this delta H, and then figure out the slope will be your delta H, or plot it versus 1 over temperature, my bad, right? ln K versus 1 over temperature. And so if you think about it right here, the slope right here is M. And what the slope is really equal to or proportionate to is this delta H of the reaction, right? The negative delta H of the reaction too as well, but R is just a constant here. So if you think about what a plot of this might look like, you can think about it this way. Come on. So we have on the left hand an exothermic reaction where this delta H is negative, and then on the right hand side endothermic where the delta H is positive, right? And you're plotting ln of K versus 1 over temperature. And so actually the first thing you need to realize is this is 1 over temperature. So you're actually going hotter from left or from right to left, right? So you're going hotter. Usually it's the other way around, but we're plotting 1 over temperature, right? 1 over 1 would be somewhere over here. 1 over 1,000 would be somewhere over here. Cool. So you're actually going hotter when you go from left to right. So you can see for exothermic reactions, as they get hotter, let's see, as T increases, the ln of K actually decreases, and thus the value of K decreases. So exothermic reactions are less and less likely to lead to products as it gets hotter and hotter and hotter, less and less likely to become spontaneous. And then vice versa for over here, as temperature increases, your ln of K actually increases, and so your value of K actually increases. And you can think of that in terms of Le Chatelier's principle, right? For an exothermic reaction, when we increase the temperature, heat is over here. And so which way we're going to shift it? We're going to shift it towards reactants, right? Towards a smaller value of K, which we can see is going on right here. And same thing for endo. You can think about that case as well. Endo, if we increase temperature, in an endothermic reaction, heat is a reactant. So you're adding more reactant as you increase the temperature, and you're going to shift towards more products, increase value of K, and it'll be more spontaneous as well. So increase or decrease the value of G. So we've been seeing a couple of these types of equations where we plot the linear form. And generally, there's also a 2-point equation. So for this one, in order to kind of figure anything out, you need to know what B is. But if you're just in case just want to know delta H, you can just plot a 2-point reaction. And so that looks like something like this: ln of K2 over K1, negative delta H of the reaction over R, 1 over T2 minus 1 over T1, right? So you can just plug and chug, figure out what you want and figure out, how to get there. So this is the 2-point equation form. In case you're curious, this is known as the Van Hoft equation, the only thing you got to be careful here is all of this stuff is temperature dependent, right? So delta H of reaction and delta S of reaction are also temperature dependent, because standard state doesn't require 25, it's just most often used. So they're also temperature dependent. And so you only want to keep your temperature range small, otherwise you're not going to get accurate information. So this 2-point equation only works in small temperature range. Cool, and that's it.